In this lecture, we will be covering sequences. And the first objective that we will focus on is writing the terms of a sequence. So before we can do that, first let's talk about what a sequence is. A sequence is just a function. We know functions take inputs and send them to outputs. So the input of a sequence is the natural numbers. Natural numbers are just 1, 2, 3, 4, 5. Counting on up. Positive integers. But when we put in the positive integer 1, it gets mapped to something we write as a with a tiny sub 1. That tiny sub 1 is using subscript notation. So it's not in line with the a, it's a little bit smaller than it. So all of these little a's, A1, A2, A3, A4. These are in the range of that sequence function. This is what's coming out. Those are called the terms of the sequence. So this here, for instance, would be the nth term. So let's look at an example where we write some terms of a sequence. We want to find the first term, A1. To find A1, I'm going to plug 1 into that expression for an. So we have 3 plus negative 1 to the 1, which is 3 minus 1, which is 2. So I know that this sequence starts off with a 2 as the first term. Let's go find what the second term is. A 2 would mean we plug 2 in for n. We get 3 plus 1, which is a positive 4. And so on and so forth. So when you're looking for the nth term of the sequence, for instance, the third term of the sequence, you replace n with 3 and see what number you get out when you evaluate the formula, and that is your term for that sequence. I'll continue in this pattern to find the first 5 terms. So I found the first 5 terms of the sequence. I'm going to put a comma and a dot, dot, dot at the end of this list before I close my bracket. Notice I did use brackets to denote the sequence. Sequences are typically written with curly brackets around them. And the dot, dot, dot here indicates that sequences never end. They go on and on and on forever because I can plug in 100, 1,000,000, 1,000, so on and so forth. I'm going to go on and find the first 5 terms of this sequence C sub n. To find the first term, I will replace n with 1. Don't need a bracket there. I got 1 squared over 2 to the 1 minus 1, which is 1 over 1, which is 1. Now I'll replace n with 2. To find the third term of the sequence, I will replace n with 3, so on and so forth. Once we compute the first 5 terms of the sequence, I'm going to continue with an ellipses indicating that the sequence never ends before I end my curly bracket. In example C, our sequence is not defined explicitly. And what that means is we're not giving an explicit formula for what the nth term of the sequence is, like we were in examples 1a and 1b. We were given a formula and all we had to do was plug into that formula to get the nth term of the sequence. Rather than being defined explicitly, example C is defined recursively. So they tell us flat out that the first term of the sequence, D1, is 25. So I do know that when I start my sequence, the first term is 25. They do not tell me a formula for Dn, they tell me a formula for Dn plus 1. Well, I would like to know, there's D1, I would like to know what is D2. What is the second term of the sequence? So if I want to find D2 and I want to use this formula here, I'd be interested in knowing what happens when n is equal to 1. Because if I let n equal 1, then I have d sub 1 plus 1. So I plugged in 1 for this end right here. So I would be finding d sub 2. Now when I go to the other side of the formula to plug in over here, remember that n is 1. So we have d sub 1 minus 5. So we found that d sub 2 is d1 minus 5. Well, we know d1 was the first term of the sequence. That was 25. And 25 minus 5 is 20. So we found that d2 is equal to 20. Now let's go find d3. To find d3, we would need to let n equal 2. So when n is equal to 2, we're looking at d sub 2 plus 1, plugging into the left side of that blue formula, which does give us d3, the third term of the sequence that we're looking for. Let's plug into the right side of the formula. It says d sub n, in this case n is 2, and we subtract 5. Well, d2 is 20, so this is 20 minus 5 to give us 15. Similarly, we continue this process to find d4 and d5, and the sequence goes on forever. Now we are going to jump to our third objective and write a pattern for the nth term of a sequence. So in our second set of examples, we start off with the terms of the sequence, and we want to figure out a formula to come up with where these terms came from. So when I look at example 2a, I can see that all of the numerators in this sequence are 1. So I can just go ahead and stick a 1 into the numerator. What is changing is the denominators. It might be helpful to point out that the first denominator is 1. So when we look at all of these numbers that show up in the denominator, if we can find a pattern for them, then we can write an expression for what to put in this denominator down here. Now, the numbers that I boxed in blue, hopefully you do recognize them as powers of 2. So what I mean is if you think about the numbers 2 to the 0, 2 to the 1, 2 squared, 2 cubed, so on and so forth, these numbers are exactly the numbers that are showing up in the denominator. So that means that generally speaking, the denominator looks like 2 to the n. Now what we have to be careful with is where this sequence is going to start. If I'm going to index this sequence to start at 1, which we have done before, sometimes the sequence may start at 0, but if I want to, my point here is that if I put 2 to the n down here right now, and I calculate a1, I would have 1 over 2, which is not the first term of the sequence. That's the second term of the sequence, 1/2. The first term of the sequence is 1. So to fix that, I want that when I plug in 1 in my exponent, I would get 0. I will shift the exponent down 1. So now if I choose the exponent to be n minus 1, then a1 would be 1 over 2 to the 1 minus 1, which is 1 over 2 to the 0, which is 1 over 1, which is 1. And then the second term of the sequence, when I plug 2 in for n, I get the 1/2 that I want for a2. So the point I want to make in this example is that you can shift a sequence depending on if you want to start at 1 or 0 with using n minus 1 or using n plus 1. Once you recognize a pattern and you see powers of 2, which is how I know I wanted to use 2 to the n, I then had to shift it because the first sequence started at 1. The first term was 1, and I'm starting my sequence at n is equal to 1. Sometimes you'll see this notation written down here at the bottom of a sequence just to indicate that it does start at 1. If you don't see that, you can assume that the sequence does start with an index of 1. We want to do the same thing in example 2b. Similar setup here because I can see that again all my numerators are 1. We need to come up with an expression for the numbers that are showing up in the denominator. Those are not powers of 2. It's not the same pattern as last time. These numbers you may not be as familiar with if you are not familiar with factorials. So a quick talk about what factorials are. I'll start with 1 factorial, which just means multiply 1 by itself. 2 factorial means multiply 1 and then multiply by 2, which would give us 2. 3 factorial means you start with 1 and you multiply up until you get to 3. So on and so forth. We'll see factorial show up again and again in our course throughout chapters 9 and 10 as we get into series. But as you can see, as we compute these factorials, these are the numbers that are showing up in the denominator. So our denominator looks like n factorial. We again have to think about if we need to shift our sequence. If n is equal to 1, then I would get 1 in the denominator, which is the first term, and so I don't need to worry about shifting my sequence over. And we have our answer for the nth term of that sequence. There was our answer. If you want to use the same notation and indicate that your sequence starts at 1, you can. But if you don't write that, I'll just assume your sequence starts at 1. Example C. Yeah, ignore this scribble right here. Example C, we want to come up with an expression for the nth term of this sequence. I just want to change my notation here. If I'm going to use brackets on the right side, I should use brackets on the left side. So I should put this here. Alternatively, I could not use brackets anywhere and just write what a sub n is, which is probably better because I'm just asking for the nth term of the sequence. But that's not that big of a deal. Looking at the numerator, that's powers of n. This is 1 squared, 2 squared, 3 squared. So not powers of n, but more specifically squares of n. So the numerator will simply just be n squared, and I am starting my sequence at 1. The denominator looks like powers 2 as well. This looks like 2 squared, 3 squared, 4 squared, 5 squared. So there's been a shift that's happened in the denominator. The shift is 1. So first thing I want to point out is the denominator is again squared because of all these 2's. We need to figure out an expression to write on the inside here that when I start with n equal to 1, I will get 2 on the inside. So I'll choose n plus 1 on the inside. Since the first term that showed up in the bottom squared was 2, putting that plus 1 will shift the sequence down to make sure that when we start it, we do end up with 2 squared in the denominator. Again, we want to write a formula for a sub n. When I look at the numerator, I do notice that all of the numbers in the numerator are odd. So I want to write an expression for what an odd number looks like. Well, an odd number looks like an even number plus 1. And an even number looks like 2 times an integer. So notice here, if I plug in n is equal to 1, I do get 3. If n is equal to 2, we get 5, and so on and so forth. So we've taken care of the numerator. Now moving on to the numbers that show up in the denominator. I do see that all of these numbers are off by a multiple. They're all off by a difference of 3. They have a common difference of 3. So let's take a look and see how we can figure out a pattern to come up with these numbers. We observe that when we subtract, for instance, 10 minus 7, 3, 13 minus 10, 3, all of these constant differences of 3 tells me that the rate of change is constant. So I know that it's linear because the first difference when we subtracted was constant. So if the sequence is linear, that means that we could write an expression for the sequence. It should look like mx plus b. just thinking about a line, I will shift it eventually back to ends and sequences, but it should look like mx plus b. We had a constant slope of 3 throughout those differences. Let's see if we can figure out what the y-intercept of that line would be. Where did that line start at? We could choose any point to plug in. So for instance, thinking about this first 7, I'm saying that when n is equal to 1, I want to get 7 out. When n is equal to 1, I want to get 7 out. So I want to get 7 out when x, in this case, is equal to 1, which implies that b is 4. So that's telling us that the line, if I was thinking about this in a linear sense, would be 3x plus 4. So in the denominator, we'll use 3n plus 4. So when you have a constant difference that shows up in the denominator, when you look at your numbers in a sequence, the numbers I have boxed in blue, and you notice that they're all off by 3 or whatever number, that tells you the slope of your line. And then you can use the first term of the sequence, how I use the 7, to figure out, well, how far do I need to shift over to start at the first term?
We're going to move on to our next objective, where we use a limit to determine whether or not a sequence converges or diverges. So starting with example 3. Above example 3, we have a definition, a formal definition of what it means for a sequence to converge to a number. We're not going to focus so much on the formal definition as much as we are going to be using this theorem in order to show that a sequence converges or not. So let's start with example, I want to start with example 3c. If I just start thinking about the values of this sequence, I'll start by plugging in n is equal to 1, and when n is equal to 2, so on and so forth. So I have a few of the terms of that sequence listed out. What we're interested in is, as we continue to list out these numbers, do these numbers eventually approach a particular value? Does the sequence tend to converge to a certain value? So I want to know what is happening to the terms of this sequence, c sub n, as n goes to infinity. What is the limit as n goes to infinity of this sequence, n squared over 2 to the n minus 1. Now we've taken limits before in calculus. We have not taken limits before of sequences. We have taken limits before of functions, which is why we have this theorem that tells us if we're interested in finding the limit of a sequence, a sub n, we can think of it as the limit of a function. I'm just going to swap out the n's for x's. I'm going to choose to rewrite this as no longer am I thinking, oh, I'm taking the limit of a finite sequence. I'm now taking the limit of a continuous function. And things like this we have seen before previously. Those are limits that we know how to take. So now if I think about what happens to the numerator as x gets very large, it goes to infinity. What happens to the denominator as x gets very large, it also goes to infinity. So now what do we do when we're met with this indeterminate form? We will now apply L'Hopital's rule, which tells us that we can again take the limit as x approaches infinity, but we need to take the derivative in the numerator, and the derivative of x squared is 2x. And we also need to take the derivative in the denominator, and the derivative of 2 to the x is 2 to the x multiplied by natural log of 2, and the derivative of 1 is, of course, 0. Now if I apply the limit again, the numerator still goes to infinity, the denominator still goes to infinity, so I will now apply L'Hopital's rule again. So we have the limit as x goes to infinity. The derivative of 2x in the numerator is 2. In the denominator, the derivative of 2 to the x is 2 to the x natural log 2, and there was a natural log 2 that was already there, so it's now squared. Notice that there's no longer an x in the numerator, so now when we apply the limit, the denominator gets very large, and the numerator stays constant at 2, meaning that the entire limit would go to 0. And so this sequence converges. Eventually, the numbers in this list eventually get smaller and smaller and smaller, and the sequence converges to 0. So essentially, when we take the limits of these sequences, we're going to use the theorem above that tells us we can switch from a sequence to a function. And then once we switch to a function, we're then able to use all of the tools that we already know when it comes to taking limits of functions, like L'Hopital's rule, for example. So let's go back and look at example 3. We're looking for the limit as n approaches infinity of a sub n. I want to know what happens to the expression 1 plus 1 over n raised to the nth power as n gets very large. The theorem tells me that I can switch this to thinking about, well, what happens to the function 1 plus 1 over x all raised to the x power as x gets very large. Now this limit here in particular is a limit back from section 5.6 when we studied L'Hopital's rule. I will insert in a link at this point in the video to show where we evaluated this limit before, but we have proven that this limit is equal to e. So eventually, as you continue to evaluate this sequence, the terms converge to e. Because we're getting a real number as our answer, I know that the sequence converges. Looking at example B, I want to know what is the limit as n goes to infinity of 3 plus negative 1 to the n. I can think of that as the limit as x goes to infinity of 3 plus negative 1 to the x. We know that as x goes to infinity of 3, the function will stay constant at 3. But as for this part with the negative 1 to the x, the function is going to be oscillating. It's going to go from negative 1 to positive 1, from negative 1 to positive 1. This is not going to converge at all. So this limit does not exist. So we've seen an example of a limit that does not exist. There's more ways that it's possible for a limit to not exist. It's possible that a limit does not exist if the limit is increasing without bound, going off to positive infinity, or decreasing without bound, going off to negative infinity. The same rules that applied with limits when we learned them back in Calculus 1 apply again here with sequences. Scalar multiple, sum or difference, product, and quotient. Now, a brief lesson on factorials. I talked about this a little bit earlier. For instance, 1 factorial is 1. 2 factorial is 1 times 2, which is 2. 3 factorial is 1 times 2 times 3, which is 6. By definition, we define 0 factorial to be 1. It is important that we pay attention to the notation here. For instance, there's a difference between saying 2 and multiplied that 2 by n factorial, which means take 2. Let's start breaking down the n factorial. We would multiply n, and then we would multiply n minus 1, n minus 2, until we got down to 3, 2, 1. Right? On the other hand, versus 2n, so the n factorial that I wrote in red, I hope that's clear. Traditionally, I've been starting at 1 and going up to the n value, like how I did here. I started at 1 and did 2, 3. I just went backwards since it started with an arbitrary n value here. But it would have been the same thing if I wrote 1 times 2 times n. Those are the exact same thing, the two lines that I have written in red. But I do want to point out the distinction between 2n factorial. 2n factorial, for instance, would mean start with 2n and then subtract 1 from 2n and continue in that pattern until you get down to 3, 2, 1. Alternatively, I could have written 2n factorial as 1 times 2 times ... 2n minus 1 until I get up to 2n. Again, those two lines are the exact same thing, but the point is it is important that we pay attention to what the factorial is being applied to, whether it's just being applied to the n or whether it's being applied to more than one factor, like a 2n. So with that in mind, let's practice simplifying some factorial expressions. Generally speaking, when you're simplifying factorials, you want to start with the larger expression and start to expand that out. So, for instance, when I look at example A here, n plus 1 is larger, so I'm going to expand n plus 1 factorial. I'll start with n plus 1, and then we multiply. We need to subtract by 1, so I'll now just be multiplying by n, and then I need to subtract by 1, so I'll be multiplying by n plus 1. And I'm going to pause here. I'm not done, because I would then need to multiply by by n minus 2, n minus 3, so on and so forth. But I do notice that this n minus 1 right here matches this n minus 1 factorial in the bottom. So instead of writing n minus 1, n minus 2, n minus 3, ... I'm going to condense all that down and just say, well, that's n minus 1 factorial, which then matches the n minus 1 factorial in the denominator so that they cancel. And I'm left with a simplified answer of n plus 1 times n. Similarly, in example B, I'm again going to start with the larger expression to begin simplifying, which is the 5n plus 2. I will drop that down by 1 and multiply by 5n plus 1. Drop that down by 1, multiply by 5n. Drop that down by 1, multiply by 5n minus 1, and I'll stop there and put the factorial on that because I see that that matches the 5n minus 1 factorial that's in the denominator, so that I'm left with my final answer as the product of these three factors.
Next, we will be using the squeeze theorem to show that a sequence converges and find what it converges to. So the premise behind the squeeze theorem is that you start off with two sequences, a sub n and b sub n, and you know that both of those sequences converge to some value L. So in theory, we're working with a situation like this. We have some sequence a sub n, the values of that sequence and then we have another sequence b sub n. And the values of the sequence b sub n may look like this. But I do know that eventually the two sequences converge to the same value, L, so where these sequences are converging out in the middle. The squeeze theorem says that you can use that to find the limit of a third sequence c sub n if it is squeezed in the middle of those two sequences. So that's what we're going to do. So we have the sequence c sub n equal to negative 1 to the n multiplied by 1 over n factorial. The first thing we would need to do is we need to find the sequences a sub n and b sub n such that negative 1 to the n, 1 over n factorial, will be squeezed in between it. Well, we can easily do that because if I need something that's bigger than this sequence, I can just choose positive 1 over n factorial. Sometimes it'll be equal. If this comes out to be a positive 1, they'll be equal. But if that comes out to be negative 1, then I'd have made sure that the right side is larger. Similarly, on the left side, I'll just choose negative 1 over n factorial. So I have that squeezed in between two sequences, a sub n and b sub n. We need to go now check this part of the theorem. What is the limit as n goes to infinity of negative 1 over n factorial? And hopefully it's the same thing. It is, as the limit as n goes to infinity of positive 1 over n factorial, and they are both 0. Therefore, I can conclude that by the squeeze theorem, the limit as n goes to infinity of our sequence, negative 1 to the n over n factorial, is equal to 0. Next, we have a theorem that tells us for any sequence, if the absolute value of that sequence converges to 0, then our sequence must converge to 0. So how can that theorem be used? So let's say that you had not thought to use the squeeze theorem in example 4. If I asked you to find the limit of this sequence, you could have started and said, well, I don't like the -1 to the n there, so instead of finding the limit of c sub n, I'm going to find the limit as n approaches infinity of the absolute value of c sub n. As soon as I put the c sub n inside the absolute value, the -1 to the n no longer matters, because when we take the absolute value of that, it will simply just be 1. So then I just have the limit as n approaches infinity of 1 over n factorial. Notice I can drop absolute value bars since n factorial is always positive. We're working with sequences, so n starts at 1. And this limit clearly goes to 0 as the denominator gets very large. So that's another way that you could have concluded that that limit was equal to 0. So this theorem is particularly handy for eliminating factors of -1 to the n. Because once you put it inside absolute value, it will simply equal 1. Let's look at example 5 where we want to do the same thing, but we need to first come up with an expression for this sequence. We don't have what a sub n is, so we need to do some pattern recognition. In the numerator, I observe that I have a sequence of odd numbers. Typically, odd numbers look like 2n plus 1 or 2n minus 1, depending on how you want to shift it. I'm going to start with 2n minus 1. Because notice that now when I start with n equal to 1, I do get the first term of 1 in the numerator. In the denominator, we have powers of 2. Hopefully we recognize that. So our denominator is not 2n, but 2 to the n. So now that we have an expression for our sequence, now let's find the limit of this. If I want to know what the limit as n approaches infinity of a sub n is, let me not forget my limit. We have a theorem from earlier in this lesson that tells us we can consider that the limit of the function 2x minus 1 over 2 to the x as x goes to infinity. L'Hopital's rule applies here because we do get an indeterminate form of infinity over infinity. So now, taking the derivative of our numerator, we have 2. Taking the derivative of our denominator, we have 2x multiplied by natural log 2. And that limit goes to 0 because the denominator gets very large as the numerator stays constant. And so we can conclude that this sequence converges. It's always converging if you're getting a real number as your answer. Next, we are going to look at what it means for a sequence to be monotonic. A sequence is monotonic if it is always increasing or if it is always decreasing. It's okay if it's not strictly increasing or decreasing. That's why we have those equal signs in there. But the terms of the sequence should either be staying the same or getting bigger, or staying the same or getting smaller. So for example, we've seen that this sequence a sub n here starts off as 2, 4, 2, 4, and bounces back and forth. So because that's not always increasing or always decreasing, this sequence is not monotonic. If I were to take a look at the terms of the sequence b sub n, we would have 1 when n is equal to 1. When n is 2, we get 4/3. When n is 3, 3/2. When n is 4, 8/5, so on and so forth. So if I were to think about the values of what this sequence is doing, just draw a rough visualization here. There's 1 and there's 2. So along the x-axis, I'm really showing n values. So when n is equal to 1, the sequence was 1. When n was equal to 2, the sequence was 4/3, which is a little bigger than 1. When n is 3, the sequence is 3/2, which is 1.5. When n is 4, we were up at 8/5. So the sequence is increasing. We can see the values of this sequence are going higher and higher and higher. This is a monotonic sequence. because it is increasing. The values are getting bigger. They're not going up and then down and then up and then down. They're always going up. That's what it means for a sequence to be monotonic. Or they're always going down. Here in part C, if I look at the terms of this sequence, I get 1 4/3, 9/7, 16 over 15. That is also a monotonic sequence. Those values are increasing. They're increasing slowly, but they are increasing. Now let's talk about what it means for a sequence to be bounded. A sequence is bounded above if there's a number that every term in the sequence is smaller than. And a sequence is bounded below if there's a number that every term in the sequence is larger than. So for example, if I consider the sequence 1 over n, I know that 1 over n is always going to be smaller than 1. Remember, we're working with natural numbers here. So I know that the sequence 1 over n is bounded above by 1. Because as we plug in natural numbers n, every term of the sequence will be smaller than 1. Then we have a theorem that tells us if a sequence is monotonic and bounded, then it converges. And that makes sense because if we think about the terms of a sequence, if I know, for example, that it's monotonic, say I know that the terms of the sequence are always increasing, but I also know that the sequence is bounded, meaning it's never going to go past some number, then eventually, if this is going to keep increasing, but it's not going to go past that number, the sequence must be converging to that number, if that number is a tight bound.